Hello students, welcome to this lecture. We're going to continue to learn a little bit more about genetics, especially we're going to talk about genetics from the standpoint of estimating what happens from one generation to the next. And we're going to answer some interesting questions. For example, we're going to look at the relationship between dominant and recessive traits and why they are more common or less common in populations. So you may ask yourself, are dominant traits always the most common? For example, we could look at these two different populations here from, this looks like maybe a sporting event where here in the United States, maybe where you've got a lot of kind of lighter skinned arms sticking up and lighter hair. And maybe this one from, I think this is probably Africa, where you've got darker skin and darker hair. In general, darker pigmentation is dominant to lighter pigmentation. And so you would expect that many people would expect that darker should then, because it's dominant, it should be more common. However, you can clearly see that by this population, lighter skin pigmentation is also very common. So let's look into this a little bit more. And the way we're going to do this is with a hypothetical situation. Imagine that we've got some flowers on this hillside, right? We have some population of flowers at 2,000 feet, and we have another population of flowers at 8,000 feet. So we have population 1 and population 2. And to simplify this, we're just going to look at one characteristic. We're going to assume that these flowers either are yellow or white. And to talk about or to represent our flowers, we're actually going to use beads. Okay, so the yellow dominant allele, which is represented by a yellow bead, we're going to also refer to that with a big Y. The white recessive allele is a little y. And so as you look into these two populations, you can quickly see, looking into the population 1, that it looks like there's a lot more yellow beads than there are white beads. And as we look into population 2, it looks like there's a lot more white beads than there are yellow beads. So I can take from this large population a subsample, a random sample from this population, and I'm going to take out 100. I'm going to take out 200 beads. The reason I'm going to take out 200 beads is because I'm going to assume that this population is diploid and that every organism, right, every individual has 2 alleles for every gene. And so in this case, I'm going to have then a total of 100 individuals. 56 plus 38 plus 6 equals 100. And when I pull out those, and I could do this 2 at a time. So I go in and I pull out 2 beads and I look at them and I look in my hand, and if they're 2 yellow beads, then that would become part of my big Y tally. And if I pull out 2 beads and one of them is yellow and one of them is white, that would be part of my big Y, little y. And if I pull out 2 beads and they're both white, that would be part of my little y tally. So I do that, I pull out 2 beads 100 times, and I end up with these counts. These can then be turned into what we call genotypic frequencies, because we can simply look at the number of big Y and divide it by the total number of individuals. So that's 56 divided by 100 equals 56%. The total number of big Y were 38, so that's 38%, and the total number of little y were 6. So I have 6% genotypic frequency. I can also say, what are the phenotypic frequencies of this sampled population? And to do this, I simply say, okay, how many of the individuals are yellow? And in order to be yellow, remember, you have to have at least one dominant big Y allele. So that means I need to add the 56 individuals that are big Y, plus the 38 individuals, which are big Y, little y, and divide that by 100, and that gives me 0.94 frequency, or 94%. And then again, the little y individuals, which then express a white flower. There are only 6 of those, and so it's still 6%. If I look at population 2, I see that it's different. When I go in and sample, I get 10 big Y, 32 big Y, and 58 little y. So my genotypic frequencies then are 10, 32, and 58. And my phenotypic frequencies, which are here, are the number of big Y's, 10, plus the number of big Y's, which are 32. So that equals about 42% of the population ends up having yellow flowers. Whereas white flowers, remember, there were 52 times that I sampled and I got little y, or 58 times, and I got little y. And so therefore the the phenotypic frequency for white color is 58% or 0.58. If I were to do this over and over again, I could essentially show you, and we could track through time, the movement or the change of these populations. And here I've broken it down into the genotypic frequencies for big Y, big Y, big Y, little y, and little y, little y. And you can see that there is a little bit of change, not much, but a little bit. And then the last two here are the changes in the phenotypic frequencies, so for yellow flower and for white flower colors. And so you can see also a slight change in thing. So why are we getting a slight change? Well, it's because this is a random sample, right, from the population. And it's expected that you would slightly, randomly get a slightly different proportion from the original population. But for the rest of today, we want to assume that that's not important. In fact, if I had the way of saying, okay, these are going to be it's an infinite population size, or a huge population, and I'm going to randomly sample a huge population sample, or in fact, if I could infinitely sample, right, you would actually see that there would be no change. Whatever your genotypic frequency was in the parental generation, that would be your exact genotypic frequency in the next generation, and that is the same for the phenotypic frequencies if we had an infinite size sample. Because we have not an infinite size, we have a finite size sample here, you do see a little bit of movement. By the way, we will talk about that in the coming lectures, and that is a mechanism of evolution where you start to see this slight change in movement. It's called genetic drift, but we're not going to worry about that in this lecture. We're going to assume that for the most part they're staying the same, and so evolution is not happening. We're not having a change in allele frequency from one generation to the next, and so therefore no evolution is happening. Population 2, again, the numbers are essentially, the same. There's a little bit of change from one generation to the next, but not enough to be concerned with at this point. So what are the conclusions we can make? Well, we can say that in population 1, we had mostly yellow beads, so therefore more big Y, more big Y, little y. And so therefore the majority of the population was yellow flower color, about 95%. In population 2, the majority of the beads were white. So therefore we had more big Y, little y, and more little y than we did of the big Y individuals. Now, because big Y, little y, though, are yellow, we still are getting, quite a few yellows, but we also have had a lot of the little y, and so, the population was, about half yellow, half white, but a lot more white than population 1. And that was going to perpetuate, through time, given that nothing else changed with these populations. If they continued to just do that over time, you wouldn't expect the numbers to change. So the proportion of dominant to recessive alleles in the population does not change, especially given this if you have an infinite population size. Now there may be these minor changes due to this random chance of slightly sampling in different proportions than the original population, but we're going to assume that these patterns were not really important in this case.